So we have seen under a Lorentz transformation the wave function entering the Dirac equation transform, and it transforms with a matrix that we call S of A, where A are the A mu nu of the Lorentz transformation for the X part. So it's a function only of that, and the other time we work out the detail of that, and we found that the generic form for an infinitesimal transformation, and then we did also for the finite one of S, we parameterize these in this manner, where this is an infinitesimal transformation, but we can do also finite one. And so instead of saying S of A, we will say S of omega is equal exponential minus I over 4 sigma mu nu omega mu nu. Okay. And omega mu nu can be, if it is infinitesimal, then you can expand and stop at the first term, otherwise it can be finite. Anyhow, what is important is the presence of these sigma mu nu that are defined using the gamma mu nu in the following manner. And what we did last time is, first we show that these are the solution for infinitesimal, and then we did also for finite one. Now, there is a surprise, and that for some transformation S is unitary, and in particular we will see that is unitary for rotation, and S of A is non-unitary for the Lorentz. Actually, we had already found out when we were doing the initial part that the Lorentz transformation in 4 dimensions cannot be implemented in a unitary way. That means unitary Lorentz transformation exists only in a higher dimensional or infinite dimensional, actually, not in 4 dimensions. And this is a confirm of that. But now we will check if this is the case. Okay, so let's start with, for example, the rotation. Well, for the rotation, we know that these parameters are just the space-time parameter, the space parameter, sorry. So the rotation, for a rotation, omega ij, this is exponential minus I over 4 sigma ij omega ij, and as I said, omega ij can be either the infinitesimal parameter or the finite parameter. For example, we find out, for example, that omega ij, if we do a finite transformation, for example, a rotation along the third axis, is delta phi times a matrix that we call In. And we built, last lecture, we built this IM both for the rotation and for the Lorentz. Okay, now let's remember that sigma ij is nothing else than I over j, gamma j. So for the rotation, if you remember, we did that, and I don't want to review all of that. For the rotation, if this is implementing a rotation, and is implementing a rotation on the space of wave function, then the index that enter here are only the space index. Okay, and then remembering that gamma I dagger is minus gamma I for the space-time, it's easy to see that sigma ij dagger is equal to plus sigma ij. Why? Because, well, if you do the dagger here, what happened is first it turned the things around, but it changed the sign of both of them, okay? And then it changed this sign, so at the end the sign remained the same, sigma ij. So let's take the S associated to a rotation, and let's do the dagger. we get exponential I over 4 sigma dot ij omega ij, and this is equal exponential, because of what we said, I4 sigma ij omega ij. But this, you see, is nothing else than the things with the plus sign, so this is nothing else than s to the minus 1. So SR is unitary. So we proved this first part. I only ask you to remember or go back and review the fact that for a rotation, these indices of the sigma and of the omega are just the space index. Okay, let's now see for a Lorentz transformation. For a Lorentz transformation, you remember, you can see from here also, the rotation affects only the space-time part, so the index here, the space part, so the index here are just the space index like we have there. Now if we instead do a Lorentz transformation, then we will have the 0i index. The 0i, because the Lorentz transformation affects the time, so there must be always a 0 index involved. Okay, so let's look for a Lorentz transformation. A Lorentz transformation, let's take a simple one, so a Lorentz, it will be exponential minus I over 2 omega sigma 0, 1, for example. Omega is a parameter of the transformation, and so I have chosen a very simple parameter to be the same for all of that, and sigma. So a very simple one, but just in this very simple one we will see is not unitary. Well, first of all, let's take sigma 0, 1, that is I over 2 gamma 0, gamma 1 minus gamma 1, gamma 0. So let's do the dagger. Sigma 0, 1 dagger is minus I over 2, gamma 1 dagger, gamma 0 dagger, minus gamma 0 dagger, gamma 1 dagger, minus 1. Then this is minus gamma 1. This is Hermitian, is gamma 0, then gamma 0 minus gamma 1, just because the gamma with the space index, the dagger gets a minus 1, while the gamma 0 is Hermitian. Okay, at least in the form that we have chosen up to now. So this object is nothing else than minus I over 2 gamma 0 gamma 1 minus gamma 1 gamma 0, so is minus sigma 0 1. Okay, so as we have these, let's take the Lorentz and let's do the dagger. Then I have I and omega. Omega, I suppose, is a real parameter. Sigma 0, 1 dagger. And this is equal, because of this relation with the minus here, is equal to I omega sigma 0, 1. And this is the same as SL. So you see they are not unitary, because here I should have had, this is different than to the minus 1. So this is the proof that there is no unitary implementation in 4 dimensions of the Lorentz transformation. But there are some nice properties. So remember that this psi was a Hilbert space element, but it had 4 components, and this S is a matrix 4 by 4. Okay, what we can anyhow do is we can prove, for example, that SL to the minus 1 is equal gamma 0, SL dagger gamma 0. So it does not satisfy the usual SL. It does not satisfy the usual SL to the minus 1 equal SL dagger, but it satisfies these, and we will prove it now. Now, yeah, to do that, let's stay very general. We will prove actually that this relation holds for also the SR. The SR, the rotation, also satisfy this relation. And this is easy to see because SR contains only sigma ij, so I can commute. I have gamma 0, SR dagger, so this is 1, SR dagger. So it's unitary and it satisfies this. So what we will do is now we will prove that a relation like that holds for all the S matrices. And this is a sort of generalization of the unitarity in the sense that you, instead of having S to the minus 1 equal S dagger, you have to sandwich with the gamma 0. Okay, so let's prove this in general. Okay, let me... Okay. So... Well, to do that, first we have to build the inverse. So remember, our goal is to prove that S to the minus 1 is gamma 0 S dagger, gamma 0 whatever is S. Okay. Now we will prove that that is exactly the relation. And of course, you know, if you then multiply by gamma 0 on the left and on the right, here on the left-hand side and on the right-hand side. So immediately from this, you get gamma 0 S to the minus 1, gamma 0 S dagger. So these are the same. Now we will prove now that the inverse always satisfy, the inverse of S always satisfy this relation. So let's, so the inverse of S. So let's do it separately for the boost and for the Lorentz. Now we know that for the rotation part, so that is what we are trying to see and see if it satisfies the first relation. We have seen before that SR is I for omega ij sigma ij for the rotation. Okay. So let's do the dagger like before. I over 4 omega ij sigma ij dagger is exponential I4 omega ij sigma ij, because this we have seen before is Hermitian, and then this one with the plus with respect to this is nothing else than SR to the minus 1. Okay, now if you don't believe that this is Hermitian, let's do it. It's very simple. Sigma ij dagger is minus I over 2 gamma I gamma j dagger minus gamma j gamma I dagger. This is minus 1/2 gamma j gamma I minus gamma I gamma j, exactly as we did before. And this is sigma ij. Okay. Now we know that gamma 0 commute with sigma ij. Gamma 0 and sigma ij commute. This is the commutator, not the anticommutator. And why? Because gamma 0 and gamma I commute. They don't see each other. You remember the relation that we have to remember is the one that says gamma mu plus gamma mu is equal to g mu nu. Okay, so if these commutes, what I can do the following things. I can sandwich. Okay, I can take this relation SR DAG, do gamma 0, and then I bring gamma 0 here, but this gamma 0, because this is made with the sigma commutes, so this is SR DAG gamma 0 square, so this is SR, okay? But now, let's see, SR is equal to SR to the minus 1, the SR, DAG. This is 1, I get DAG. So from this relation, I get SR to the minus 1. That means gamma 0, SR DAG, gamma 0 is equal SR minus 1. So SR satisfied the relation we wanted. Now let's see if this works also for the Lorentz. For the Lorentz, again, let's take as before a simple transformation of the form exponential minus I over 2 omega sigma 0 1. And then S DAG is equal exponential I over 2 omega sigma 0 1 DAG. And then this 0, 1, the DAG change sign. We have seen it before. Exponential minus 1 over omega sigma 0, 1. And this is S. Now, again, let's see why sigma 0, 1 change sign. Sigma 0, 1 DAG is I gamma 0, gamma 1. All this DAG. Minus gamma 1, gamma 0, DAG, and this is, okay, this change sign, so I have minus I over 2, then gamma 1, DAG, gamma 0, DAG, minus gamma 0, DAG, gamma 1, DAG, but this is minus 1, it absorbs this 1, so I have 1/2, gamma 1, gamma 0, minus gamma 0. Here there is a minus, I bring it there, gamma 1. And so this is equal to minus sigma 0, 1. Okay, that is what we wanted to prove. Well, that is not the end of the story, because now what we have to prove this relation, one of these two relations, okay, either that one or this one for the sigma. So we have only this. Let's build, sorry, is sigma 0, 1. Oh, that is you can do as an exercise, it's very simple, okay? Please. I have answered. You did not understand? I have answered. I have answered. Sorry that I pull your leg. Shout, shout. Because I'm deaf.
So the rotations are included in Lorentz transformation?
The rotation, yes, of course. The Lorentz transformation means rotation and boost. Okay, so when I talk about Lorentz transformation, I always include the rotation. No, I have treated the rotation here and proved the relation we wanted to prove. Now I am treating the Lorentz transformation. And that this is a Lorentz transformation is indicated by the fact that the generator is sigma 0, 1, so it involves time and space. So this is just a boost along x. No, what? Oh, separately because it's easier. It's easier in the sense that we treat it separately because also the hermeticity property of the sigma are different. You see, this one were Hermitian, while that one are not Hermitian, this one. So we are treating separately because the sigma involved are different and have different hermeticity property. Okay, that is the reason. It becomes more complicated to treat all of them in a stroke, but at the end, they both satisfy this relation. Okay. Now, another thing that I want to show is that gamma 0, I need that sigma 0 I is equal minus sigma 0 1 gamma 0, and this is very simple to prove. Gamma 0 sigma 0 1 is I over 2 gamma 0 gamma 0 gamma 1 minus gamma 0 gamma 1 gamma 0. So I am doing this, just this is the definition. Now I can bring I over 2. I can bring this on the left-hand side because it changed sign twice, so it remains gamma 1, gamma 0, minus this one I leave as it is, gamma 0, gamma 0. But now this object, if I bring the gamma 0 that is here out, is sigma 0, 1, gamma 0. Okay, sorry, sigma 0, 1, gamma 0. But the sigma are antisymmetric in the two indices. So this is sigma 1, 0, gamma 0. Sorry, this is sigma 1, 0. So this is sigma 0, 1, gamma 0. Okay, so this is the proof. What did I do? Gamma 0 is here. I brought in the the sigma 0, 1, that is I over 2 gamma 0, gamma 1, gamma 1, gamma 0. And then I start playing with the gamma. This is always the trick with these things. So I bring the gamma 1 on the left, and I change sign twice, so altogether is plus. Here I leave everything invariant. Now I take this expression, and I can pull out the gamma 0 on the right. What is left is sigma 1, 0. But sigma 1, 0 is the opposite because it's antisymmetric of sigma 0, 1. And so I get this relation that is this. Now, why I do need all this transformation? I need all this transformation because let's take the following thing, gamma 0 as dagger, and let's take for a Lorentz one. So remember this was the exponential over there, so as it is the exponential, it is an infinite power sum, is this series. Okay. Gamma 0, so this is the sum. Okay, now what do I do? Because here I have a lot of things to pass through. Well, what I do is the following things. Sum over n to infinity. I take one of them, minus I over 2 omega sigma 0, 1. And before inserting the other, I insert gamma 0, gamma 0. Why? Because this is 1 after all. So I can do minus I over 2 omega sigma 0, 1. And then gamma 0, gamma 0, and so on. I go on in this manner. Okay. Now, I have seen that gamma 0, when it passed through the things, it leaves a minus sign. So basically I've inserted one. Now let's look at these things. If you make this pass through, okay, it changes sign. So you get all these things with change sign, and the same the other things. So basically what you get is n from 0 to infinity I to omega sigma 0, 1 n. Okay, so what I have done is I brought this on the other side, and then it changed sign. So you get a plus. The gamma 0 give me 1, and I do that for every one of these. In that manner, I eliminate the gamma 0 that I had at the end, but the price I paid is that here I got a plus sign. So this is SL to the minus 1, and I have proved what I wanted to prove. Okay, so let's just summarize the things. No, the A's associated to rotation are unitary, but the A's associated to a Lorentz transformation, they are not unitary. But both of them satisfy this generalized unitary transformation. Okay? For the rotation, this is trivial because the gamma 0 passed through the rotation because it's made only of sigma I, and so you get gamma 0 square, and you get the usual unitary transformation. The gamma 0 does not pass through if you have a Lorentz transformation because it's made with the sigma 0, 1, and then you have to be careful. So this is satisfied by every transformation, but not by every transformation, the rotation and the things. The rotation satisfies the further things that they are unitary. So if these were rotation, then we would get this also, and this is a consequence of this. But this is the generalized one satisfied by every one of these transformations. Now, another important things, there are this subtlety that people don't usually pay attention to, but that they are something important. Now, another subtlety is the four currents that we had with the Dirac and its covariant form. Let's bring the four currents into a covariant form. But if you remember, we have the density matrix that was psi daga psi, and we have the Ji that was C psi daga alpha I psi. This was the four current. Now let's try to bring them in a more uniform thing. So let's call this was the thing. Let's call J0 as C rho. And this one, now we can write note C psi daga gamma 0 psi. So I've put the C because there is a C on the space part, so I put a C also on the time part. Second, I put here an identity, gamma 0 is the identity, is like this. But then this becomes C psi bar gamma 0 psi. Okay, now let's see a very similar form for the J0. Here they did not look similar at all. There was no alpha, no beta, no gamma here. There was no C, but now introducing this object, I got a form that has a C and has a gamma 0 like the index here. Let's take the Ji. We have C psi daga alpha I psi is C, psi daga, not psi bar. This is psi daga. Now let's write the alpha I. Let's remember the alpha I could be written as gamma 0 gamma I psi. Okay, so then this object is nothing else than psi bar. They get the gamma I, they get psi. Okay, so I have only rewritten these in this form. And when we introduced the gamma matrices, we already proved this relation, that the alpha I are gamma 0, gamma I. Okay, so now you see that there is a very uniform form. Let's look at this extreme end side. They have the same a C in front of both of them, and second, they have the gamma 0 here and the gamma I here, like their index, 0 and I. So they have a very uniform form of this. Now, I will show to you now that this object that I can compactly write as C psi dag gamma mu psi, that this is a 4 vector. Okay? So that means it transforms as a 4 vector. Let's take the transformed one. The transformed one, it will be C psi dag prime gamma 0 gamma mu psi prime x prime. This is basically my this is my psi dag psi bar prime. Okay, so now let's do the transformation. So I transform this, I get S dag S, then I have gamma 0 gamma mu S psi of x, or psi. Okay, so this object is this. Now let's use the relation that we have written there, and then, okay, if I use this relation, let's see which one, this one, I have that if I use this relation, let's multiply on the left by gamma 0. I get gamma 0 s to the minus 1 equal s dag gamma 0, or S dag gamma 0 is equal gamma 0 s to the minus 1. So here, S dag gamma 0, I replace with gamma 0 s to the minus 1. I have psi dag gamma 0 s to the minus 1. Then I have gamma mu s psi. Okay? So I have replaced S dag gamma 0 with gamma 0 s to the minus 1 using this relation. Now, you see here what you have. You have s to the minus 1 gamma mu s. But you remember one of the constraints when we start building the s, one of the constraints that we had for the s was the following one. If you remember, okay, let me write it here. One of the constraints that has to satisfy in order for the Dirac equation to be covariant was the following one. Let me just try to find, it was the following one. S to the minus 1 gamma sigma s, it was equal to A sigma nu gamma nu. That was one of the constraints that S had to satisfy for the Dirac equation to be covariant, okay? Remember. Then let's replace here that quantity. That means we get C psi dag gamma 0. Here I replace with that quantity. Now instead of sigma I have the index mu, so I will get A mu nu gamma nu, and the s have disappeared, psi. Now these are numbers, so I can bring them out, and I have A mu nu C psi dag gamma 0 gamma nu psi. This is equal to A mu nu. This object is a psi dag, psi bar, so I have C psi bar gamma nu psi. But this is the 4 current, so this is equal to A mu nu, j nu. So we started from here and we proved that relation. That means that this strange object that we built and we manipulated it in order that it has the same form for the time and the space component, that means just C, and that here I have either gamma 0 or gamma mu, is so that strange object that is the covariant, the four currents, really transform as a vector. You see, like a space vector with the A. Then if this is a very important point, that if you build the four currents, this transform as a four vector. You know, it might be, I don't know, but it might be that in the final exam I give something that I've already done in class, like prove that the four currents transform as a four vector. Just an example. So it might be that I give something that we did in class, but you don't have the book to copy it, so you have to think a little bit and to see how to do. Now, another point is that now that we have this, and we have seen that this satisfies a four vector, if I do the four conservation law, this is a covariant equation, in the sense that this transforms as a vector, this transforms as a vector, they are saturated, and this is in a covariant form. That means if I go to a new frame, it will be j prime mu over dx prime mu equals 0. So in a new frame, the form of the equation remains the same. When I say covariant, it means the form of the equation remains the same. But it remains the same only if you know the transformation property of each. And I know that this transforms as a vector, and I've proved that this transforms as a vector. So this altogether is not something that we don't know transform. We have seen. And then when we change, it goes into this equation. So, you know, the covariant properties are very nice, because once you have written everything in terms of covariant form, covariant object, then you know the form of the equation remains the same. But if not, then if you have not written in terms of covariant form, then okay, any question? So somehow what we have done over the last previous lecture, but maybe we will, this week we will do something new and then we'll stop. Next week maybe whatever you ask me to redo, I will redo, especially regarding the Dirac equation, because the Dirac equation will be the central of the final exam. So concentrate, if you are still reviewing Lorentz transformation, time dilation, and so on and so forth. There is much more material on the Dirac equation, so please do concentrate on that. Also on the question that I expect that you tell me what to review next week, okay? So we have seen which are the transformation S on the wave function once the space-time transformation is the Lorentz one induced by A mu nu. We have seen that this S for the rotation as is unitary, but not for the Lorentz transformation, but it satisfies, in both cases, satisfies this generalized unitary transformation. I call generalized because it's sandwiched between two gamma 0. If there were no gamma 0, then this would be unitarity, okay? Now, the next step is to see, now we have done the Lorentz, and we did not put any constraint on the Lorentz, so it could also be an improper Lorentz transformation, like the improper are those that contain space reflection, for example. So let's see what happened for space reflection. And we have the form of the S now, but we don't have the form, for example, of what how space reflection is implemented at the wave function level. So let me keep this. So now what we will do is space reflection. Now space reflection, it means the x goes into minus x. By x I means the xi, so all three of them, while t remain the same. Okay. It is part of the Lorentz transformation. Why? Because the Lorentz transformation are all those transformations that maintain the fourth length, the one with 4 component invariant. That means is the one that keep invariant c squared t squared minus x squared minus y squared minus z squared. These 4 distance, every transformation that keep these 4 distance invariant is a Lorentz transformation. So to come to your things, the rotation leaves this part invariant, don't touch this, so the rotation is part of the Lorentz transformation. Only the part that is the transformation with the velocity we call boost. Maybe you got confused because at the beginning I called that Lorentz transformation, but just it was a sort of not proper manner. I should have called boost the transformation in which there is the change of frame. Okay, now this one preserve that distance. So this space reflection is part of the Lorentz transformation. And if it is part of the Lorentz transformation, it must have an mu nu. That means a matrix for the Lorentz transformation. Remember that this was mu nu x nu, the Lorentz transformation. So as this is a Lorentz transformation, because it preserves the 4 distance, it must have an nu mu. But which is the matrix that does this? The matrix does this is 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1. Okay? And note, these strange things is the same as the metric, but with the index up. You can say, oh, but here you have one index up and one index down, and here you have both index up. Yes, these, this object is this, but this object also is this. And this object is this only when the index are both up, because if I bring one index down, I know that if I bring one index down, then this is nothing else than the d mu nu, because I bring an index down, multiplying by the metric, then I get all this index get plus 1, okay? And so I get the Kronecker delta, because I get this from this. G mu nu, I want to bring an index down, I have to do like the following, nu sigma, okay? And then this one, I get an object that is mu sigma. But multiplying 2 matrices like that, even if one has the index down, both of them down, I get all this sign plus. So this is delta mu sigma. I do this simple exercise because these are very important. So here, this quantity has 2 representations. One is a metric with both index up, and another as the space reflection. So don't be confused that in the book the author does not say nothing on the fact that here there is one index up and one down, and here there is 2 index up. It's correct. It means it's the same quantity. Now, if you remember, we wrote down there that this is a special element. Now, what we want, the space reflection is this. The goal, which is our goal, we want to find the matrix that implement the space reflection on the wave function, on the Dirac wave function. Okay, like we did before, we had the Lorentz transformation and we found which is the S. Now, as the space reflection is part of the Lorentz transformation, the element that will implement the space reflection at the wave function level will satisfy this relation, the same relation, the usual relation. We knew that the S that implement the Lorentz transformation at the wave function level has to satisfy this relation, and this came out from the requirement of covariance of the Dirac equation. So if this also is what we want, let's call instead of calling S, this S is for a generic Lorentz transformation. Let's call P the one that implement for space reflection. Then we have A nu mu gamma mu equal. So P is the operator which implements space reflection on the psi. So it has the same role as S, but only for the space reflection. Let's call it P. Now let's multiply on the left by A sigma nu. So let's multiply on the left this expression for A sigma nu. We have A nu mu gamma mu equal A sigma nu P gamma nu P to the minus 1. So I've just copied this, but instead of calling S, I call it P because it's just for the space reflection. Now, let's remember the relation between these A. The A are orthonormal because the A preserve this length, so they are orthonormal. So this object is delta sigma mu gamma mu equal A sigma nu P gamma nu P to the minus 1, this object. But it means gamma sigma equal A sigma nu P gamma nu P to the minus 1. Now, let's remember that the A associated to space reflection, it was like the G. So here it is summed, but I can write these as the following things. I take, these are numbers, so I can bring wherever I want. I take P and bring it here. And these I call, they are summed over nu, but nu is in the right position, so I don't have to put the symbol of sign. They are crossed with this other. But now I replace A mu nu here with G. Why? Because for the space reflection, the A associated to the space reflection is the same as G. So I have P, G, sigma nu, gamma nu, P to the minus 1. A very strange relation. But now, because the index are not crossed, I have replaced this with this. Okay, like I know from here. So now I indicated that the index is summed over this. Okay, so I get gamma sigma is equal to this relation. But now let's go and see it in details, what this relation mean? First of all, let's multiply both sides. Let's multiply the right-hand side by p to the minus 1. So the left-hand side by p to the minus 1 and the right-hand side by p. Okay, so if now I multiply by p to the minus 1 and p, what I get is the following things. I get p to the minus 1 gamma sigma p, that is this. P, I multiply everything from the left by p minus 1 and from the right by p. Then this gets sandwiched between p minus 1 and p. They get this relation. The other one, this one cancel this and this one cancel this, so I get equal sigma g sigma nu p nu sum over nu. Okay? So let's take, please. This is a new. Oh, bravo. Gamma nu. Okay, let's for example choose sigma equals 0. Then we have p to the minus 1 gamma 0 p equal sum g0 nu gamma nu. But this g is different from 0 only when nu is equal 0, right? So there is only a g0, 0. So this is g0, 0 gamma 0, and this is 1. So this is equal gamma 0. So I have a first relation that is p to the minus 1 gamma 0 p is equal gamma 0. Okay? Let's remember this. Then let's choose a sigma equal I. If we choose sigma equal I have gamma to the minus 1, p to the minus 1, gamma I, p is equal, here I have sigma equal I, so the only things that are, the only g that are the same are those that have the same index. So I have g I gamma I. And remember, I have chosen sigma equal I, so this is not sum. This is just, suppose I chose 3, this is g33 gamma 3. Nothing is summed here, okay? You understand why? I have put I, but which is the only g that is different from 0? The one that has the same value, because only the diagonal one. So I have I, and then nu is I, then gamma E is I. And well, we know that the gii are minus 1, so I get p to the minus 1 gamma I p equal minus gamma I. This is the other relation. So I have found, at least at this moment, all the p act on gamma 0 and on gamma I. The space reflection does not change gamma 0, but it changes gamma I. And that is what you should do, because, you know, what we expect, because after all, the gamma mu are like, after all, they are like vector. So now, let's go back here. Let's cancel this part. And we have to find a p that satisfies these two relations. So I have to find a p. Now I can cancel, actually, everything. These are the two relations that have to be satisfied. Now, there is a solution, yes. It's simple to find a solution to that two equations. You can multiply by a phase, I phi, any phase I want, an arbitrary phase, times gamma 0. It satisfies those relations. Let's go and check. Okay, now let's remember how gamma 0 is. Let's write them here. Gamma 0 is, at least in the notation we have used up to now. Tomorrow we will start seeing other notation, the Majorana one and the Weil one. Now you see that gamma 0 to the minus 1 is equal gamma 0, and you see immediately which is the gamma whose inverse multiplied by gamma 0 give me the identity, is the same. Okay, so the inverse is the same. So now let's see if this solution, so this is my solution, proposed solution. I've not derived it explicitly, but let's see if it works. So let's start from this one. I have P, we have to verify if this solution satisfies this equation. Now I have P to the minus 1, it means exponential minus I gamma, I phi, gamma 0 to the minus 1, gamma 0, then here I have I phi, gamma 0 is equal gamma 0. So I have to verify if this is satisfied, it's the first relation. The I phi goes away, this one goes away, and then I'm left with gamma 0. So this relation is satisfied by the choice of P like that. Let's see the second one. Second one is P to the minus 1, gamma I, P0, it has to be equal minus gamma I. Okay, I take the same things, I have I minus I phi, but instead of putting gamma 0 to the minus 1, I know that gamma 0 to the minus 1 is gamma 0, so I put gamma 0, gamma I, A phi, gamma 0. So this object is this, then I have gamma 0, then I have put this equal this. Okay, let's see what is equal this quantity. The phase disappear. Then I can exchange gamma 0 and gamma I, but I know that I get a minus sign, so I get minus gamma 1, gamma 0, gamma 0. But gamma 0 squared is the identity, so I get minus gamma I. That is exactly this. So also the second one is verified. So that is the implementation of the space reflection on the wave function. This is very important. Now, the phase is still not uniquely determined. Can I fix a little bit? Well, usually I prefer to leave it undetermined. This phase, that means the operator that implements the space reflection on the wave function is the gamma 0 modular phase. But some people, and also the book, does the following things. He says, well, you know, the psi are like spinor. We have seen that S had I for sigma mu nu, and there was this for, that means you have to do a 4 pi rotation to come back to the same thing. So the wave function of Dirac are spinor, or sometimes they call them bispinors, but because they are 4 2 by 2. So what they do is they say, okay, if I want something that once I do 4 times I come back to the same things, that means, by the way, P is something like if I'm in 1 dimension, the space reflection is like a rotation of pi. Okay, so they say if I do P 4 times, it means I for phi gamma 0 to the 4th psi. Okay, so if I do 4 times, is something like doing a 4 pi rotation, and I know that with a 4 pi rotation I get back to the same things. So let's do 4 pi and impose that we get back to the same things. That means we impose that this is 1. When this happens, well, this is 1, but we have A for phi, it has to be equal psi. This one has to be equal to 1, and then what happens is that this happens only if I phi is equal to plus minus 1 or plus minus I. And so it determines which is the angle. The angle can be any of these 4 values. I don't particularly like to make a choice for the space reflection, but for the phase of the space reflection, but still now let's even if we don't do a choice, let's anyhow go back and see how it acts on the wave function, because we know P is the analog of S for space reflection, and it must act on wave function. Okay. Now let's remember how gamma was. So let's take it this way. This is the solution. And we know that gamma 0 in our representation was this one, at least in the representation that we have used up to now, that we will call Dirac representation. Then let's see. We have psi prime, x prime, t prime, okay, and this is psi prime of minus x times t, because this is the space reflection, and we know it is p on psi xt. This is the operator. But the operator is nothing else than I phi gamma 0 psi x of t. Now, so this is the action. Let's remember that this is a 4-component object, so we will have A phi, then this matrix, and then we have psi 1, psi 2, psi 3, psi 4. Okay, and here we will have the same. We will have psi prime minus x1, psi 2 minus x, psi 3 minus x. I did not put t, but let's put t so that we indicate that it does not change. Okay. Then from here you see immediately the first two components just remain the same. So I have that psi 1 x of, or I can put in this manner, P psi 1 is I phi psi 1. It does not change anything on psi 1 except the phase. Pi on psi 2 is I phi on psi 2 because it's all identity. And then, so this object, remember this object is pi on psi. Pi on psi 3, here is the difference. Now you have minus I, so you get A phi psi 3, and P on psi 4 is minus E phi psi 4. So the two lower components change sign, modulo a phase, under space reflection. The first two don't change sign. Okay, so just to summarize this part, space reflection are part of the Lorentz transformation. We had found the general matrix S that tell us how Dirac wave function change under a Lorentz transformation. We ask ourselves, how do we implement on the wave function the space reflection? Do we simply change? No. We have to multiply by a matrix, and that matrix we found using the constraint that the S and also P has to satisfy must have this general form, a phase multiplied by gamma 0. You know, it's not something complicated like the S that was exponential minus I over 2 sigma mu nu, omega mu nu, and so on. It's something very simple. But still, it's a 4x4 matrix, like it has to be. How does it act on the things? Well, it multiplies by a phase the first two components. The other two components, not only it multiplies by a phase, but it changes sign. So this is the consistent manner in which space reflection is implemented on the Hilbert space. Why I say consistent? Because it's consistent with the fact that they are a Lorentz transformation. They belong to the Lorentz transformation. Okay, now you have seen these gamma matrices, and these matrices are 4 by 4, so they have, can I cancel? Everything up to this moment is in the book. And now tomorrow and the day after, I will only pick some part and tell you which pages I am picking up of the book, okay? Because otherwise I will jump and skip several things. So for example, I'm skipping most of a chapter. But now, up to now, what we have done today is so today we have done the end of chapter 3 and chapter 4, but chapter 4 is just 2 pages. And now we will start chapter 5. After that, we will skip many things, and I'll tell you just read the pages from this to that, and so on and so forth. So, okay. So we consider this space reflection finished. I hope to be able to do also time reflection and charge conjugation. They are a little bit more complicated, and I need to introduce the formalism of the Dirac Hall formalism and so on. I don't know if I will have enough time, but we will do what we can do. Okay. Now, as we said, the gamma mu matrices are 4 by 4 matrices. They have the form that you all know. That means the gamma 0 is I 0 0 minus I, and the gamma I are sigma I minus sigma I 0 0. Am I correct? I don't use this very much. I use the Majorana things, and we will do it, but so I always have doubts. Yeah. Okay, but these are 16 elements. So, you know, that if I consider how many out of these I can build linearly independent, that means if you say you have just 4 gamma matrices, but how many linearly independent matrices you can build? You can build 16, because, you know, as they are 4 by 4, I could do 0, 0, 0, 0, 0, 0, 0, 0, 0. This is one. Then I can do another one. And so on, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. You understand what I mean? And so on. That means you put a 1, and then you get 16, and they are linearly independent. So out of these, I should be able, by doing combination of them and so on, to build 16 linearly independent. You can say, well, you use these and fine, but every time you have to write. So somebody, that was Pauli, built which are the 16 linearly independent matrices that you can build out of these. And they are the following one. First of all, equal, so remember they must be 16 and they must be linearly independent. What Pauli did, he built these 16 linearly independent matrices that you can derive from these, but he preserved many of the properties of the gamma matrices, and he built them out of the gamma matrices. So for example, he built one, by the way, he called them gamma n. we will see now what n stays for. Okay, he built a scalar one, and is the identity. The identity is one of those 16, right? Then he built the vector one. And oh, by the way, how many are the scalar one? Just one. Then he built the vector one with an index mu, and these are the gamma mu. They are vector because we know that the gamma mu transform like vectors. Okay, and there are 4 of them. Then he built the tensor one. So I put S for scalar, V for vector, T for tensor, mu nu, and he built them as the sigma mu nu. How many are of them? They are antisymmetric, remember. They are antisymmetric, so we will have that the 4 diagonal one are 0. Out of 16, then 4 are 0, we are left with 12, but they are antisymmetric, so the independent one are just 6. And then he built another one, the pseudo-scalar, that is the following. I, gamma 0, he called it gamma 5, and is defined in this manner. It's the first time you get the gamma 5, but it's very important, and we will see. I, gamma 0, gamma 1, gamma 2, gamma 3. And then he built a pseudo vector, or an axial vector. So this one is also 1, and is called pseudo-scalar. As it is not a scalar, but there is this pseudo, it means under some transformation it will do strange things. And then he built a pseudo vector that is gamma 5, gamma mu, and these, how many are these? These are 4. And this is a pseudo vector. So altogether we have 16, 5, 11, 12, 16. So we have 16 matrices that are not the trivial 1, 1, 0, 0, 0, 1, 1, and so on, but they are built in this manner. Well, of course, now you have to prove that they are linearly independent and some properties. Well, there are a set of properties that these gamma matrices have, and we will indicate some of them. Okay, the first property, there is a set of property, and then we will prove. All of these have the following feature. First feature, the gamma, whatever it is, when you do the square, you get plus or minus the identity. That is very nice because it is a property also of the gamma matrix. If you remember the gamma matrix, when you do the square, you get the identity or modulo sign. So all these gamma, whatever is gamma, I did not put an index. When you do the square, you get plus or minus 1. Second property, then we will go on and prove some of them. Second property, if you take a gamma n, any of these, you can for sure find, so the statement is given a gamma n, you can find at least one gamma m such that gamma n, gamma m is equal minus gamma n, gamma n. Sorry, I put among parentheses because this is not a power, but it's an index. So it means you give me one of these 16 gamma, I can guarantee to you that I can find at least another one that anti-commutes with this, okay? So this is another very important property. And the last property, well, no, there is another property, but let's first write this, that given gamma n, or given a gamma A and a gamma B, it is possible to find gamma n different from the scalar one, such that gamma A times gamma B is equal to a number FAB n gamma n. Okay, that means you give me the product of two, and I can always reduce to a number by one of them. Okay, so if you give me the product, if you give me two, do the product, you can always reduce it to one with some coefficient in front. Okay, so this is another property of this. The last property is not the last one, the trace of any gamma n is equal 0, so they are all traceless. And the last one, they are linearly independent. That means sum an gamma n equals 0 implies the an are equal 0, so they are linearly independent. So I have 16 linearly independent, and they are what I wanted. They are linearly independent. Now I don't have any space where to work, but these are the properties that they have, and now we will go and show some of them, okay? Where should I write?
Sorry?
Yes.
I think the trace of, I think it's just for one of the figures, maybe.
You might be right.
So it becomes the scalar one?
Except the scalar. So gamma n different from the scalars. Okay, otherwise it is 1, of course. So it is 4 actually. So let's see. Okay, let's see if we. Yes. Shout.
What do we mean when we say scalar?
Scalar is this.
What did you say? 4 by 4 matrix?
Is the identity matrix. So we call it scalar for the reason that the identity matrix remains on itself if you do a Lorentz transformation. Okay? So we call it, they call in the literature scalar for this reason. It's the identity matrix. Okay, that's the only reason. Now let me write them in. Horizontally. So I have gamma nu mu equal gamma mu, gamma t mu nu is equal sigma mu nu, gamma p is gamma phi, that is I, gamma 0, gamma 1, gamma 2, gamma 3, and gamma axial is gamma mu, gamma mu. Okay, so these are the matrices. Now I have space to go on and prove what I want to prove. Okay, we will only do examples of this proof, okay? So for example, the property A, if you do on this, is trivial. To the square, it gives you the identity. Or let's take, for example, gamma mu. So let's see if the vector 1, when we do the square, what we get? We get gamma mu square. But this is equal to gamma mu plus gamma mu over 2. But from the relation that the gamma mu satisfies, this is nothing else than g mu mu over 2, where mu is not summed, it's just indicated there. And this is what it is. This object is 1 if mu is 0, or is minus, by the way, times the identity matrix, because these are 4 by 4 matrix, so there is this factor times the identity matrix. Minus 1 if mu is equal I. Okay, so we get this plus and minus I. So this is satisfied. We can do also, for example, let's do for this. Let's see if so we have done for this, let's do for this, for the tensor. Let's see if the tensor square gives me the identity plus or minus 1. So I take the tensor 1, mu nu, I do the square. This is sigma mu nu square. This is I over 2 gamma nu minus gamma mu square. This is equal 1/4 gamma nu minus gamma mu square. This is 1/4 gamma nu minus gamma mu minus gamma mu is equal, let's do all the product, and we get 1/4 gamma mu minus gamma mu minus gamma mu plus gamma mu. Okay. Now we start inverting here. For example, mu and nu we invert, we get 1/4 gamma mu, this one. Then we invert these two, and we get minus gamma nu plus 2g mu nu, and then gamma nu minus, let's take these, and let's now let's take these. No, we do nothing on these. Gamma mu. Okay, but you see this one and this one are the same. Why? Because mu and mu are summed. Nu and nu are summed, so it doesn't matter if you call them mu or nu. So you can put a 2. This one and this one are the same. And then on the last one, we instead exchange these two. Then we get plus gamma nu minus gamma mu plus 2 g mu nu gamma mu. Okay, now you can, this object now becomes minus 1/4 minus gamma mu square plus 2g mu nu gamma mu minus 2 g mu gamma nu square minus gamma mu square plus 2g mu nu gamma mu. Okay, now there are various things that are the same, that are this one, and this one. So I get 1/4, and then I get minus 4 gamma mu square Then I have the 2g mu nu, so they have 2g mu nu gamma mu plus gamma mu Okay, well, this one, each of them you can write as gamma mu plus gamma mu over 2. This one is gamma nu times gamma nu plus gamma nu divided by 2. And as the anti-commutator are equal to g mu nu, what you get is from here there is a 4, so you get G mu mu, G nu nu, the identity, minus, then this one you know, so there is a minus, and here there is a 2, G mu nu, a 2 here, it cancels the 4, it remains only the minus, G mu nu, times the identity. And now this object for, let's say, mu equal nu is equal 0, okay? But we know that sigma mu nu, when mu and nu is equal 0, is 0. So that means this quantity, if it is 0, of course, a square cannot give you 1. And if instead mu is different from nu, then you get G mu mu, G nu nu, times the identity, and this, according to if mu is 0 or if mu is I, is the identity like we wanted. Okay? So we have proved, at least for 3 of them, we have proved the first expression. Just this is a lot of gymnastic with the gamma, and I invite you before the exam, beside reviewing the theory and understand everything, to do a lot of gymnastic with the gamma, because another small exercise can be on the gamma. Okay, because you see, remember the property of the gamma, and then now let's check the property B, that given a gamma A, there is at least another gamma such that it satisfies that quantity. For example, let's take these things. Let's take, for example, gamma nu. Then we know that there is a gamma mu with mu different from nu, such that gamma nu plus gamma nu is equal 0 if mu is different from nu. Okay, so we have verified the B, at least for this quantity. And we can verify also for this one, which is, given sigma mu nu, the matrix among these that commutes with that, anti-commutes with that, there is a minus. Well, what happens is easy to prove. The sigma mu nu and gamma mu, their anti-commutator is 0, so sigma mu nu, gamma mu is equal minus gamma mu, sigma mu nu. So, which is the partner that anti-commute with when gamma n is sigma mu nu, is nothing else than gamma mu. Now let's see, using this property, these two properties, let's prove this. So we skip for the moment this, let's prove this, because it's easy now to prove that one, and then we stop here. Tomorrow we will continue with the rest. Okay, let's use B. We have gamma n, gamma m is equal minus gamma m, gamma n. That means at least we know that there is that. Then let's multiply on the left by gamma n. Then we get gamma n square, gamma m equal minus gamma m, gamma n, sorry, okay, now this is the identity, gamma m. Now let's take the trace on both sides. So I have trace, the identity, gamma m equal minus trace, gamma n, gamma m, gamma n. But the trace have the cyclic property, so this is equal to trace. I bring this on this side, gamma n square, gamma m. But this is the identity, so this is trace, gamma m, because this is the identity. So you have trace gamma n equal trace minus gamma n. From this I get the trace gamma n is equal to 0, except when it is the scalar. Okay, let's stop here. Tomorrow we will work out these other two properties, because especially the last one is very important.